Hello everyone. I'm very excited in participating in the PPC 2022 conference, and I'm very glad to be here to share some of my recent works, which is about the manufacturing micro and nanostructures via controlled fragmentation induced by co-drawing of ductile-brittle composites. My collaborators, Professor Gao and Professor Wei, directed this project, and Dr. Wang and Dr. Chen did most of the experimental parts in this work. So next, I'd like to introduce this work in the 4 parts: the background, the main method, some discussions, and finally the summary. So first, as we know, co-drawing is a widely adopted processing approach for fabricating large aspect ratio structures in industry. And actually, it also plays very important roles in our daily life. For example, these wheel spokes and these steel tubes, and also many types of polymer fibers. Co-drawing technique has a long history, and it experienced fast development since 1920s and the 1930s, when it was found to be able to enhance the mechanical properties of polymers by researchers like Carruthers and Hill. Traditional co-drawing techniques basically apply to processing in micro scale. Then we are interested in whether it can also contribute to micro and nano technologies. Actually, in micro and nano devices, there are also many large aspect ratio components like these nano rods and nano wires in this high performance gas sensor, and these nano ribbons in this skin conformal tactile sensor. However, existing methods suffer from different problems in mass production, like high cost and complex operation. Recently, our collaborators discovered a novel microfabrication method based on co-drawing. For example, first, we can prepare a long fiber of a core cladding structure like this and apply uniaxial tension. Since the cladding is made of some specific material, so it will experience necking under tension. And as the neck propagates, we will find the core will fracture sequentially, just following the neck propagation. So this phenomenon can also be observed in this film substrate system. And even after we etch out the cladding and the substrate, the ductile material in this structure, we can obtain large amount of these micro rods and micro ribbons. So basically, this provides us a fast, inexpensive, simple, and upscalable fabrication method for micro and nanostructures. However, so far, most of the investigations in this field are from experiments. And here we propose a theoretical work to help us better understand this phenomenon and guide further experiment. If we look into this local area near the neck, it's easy to identify a shear leg zone where the load is transferred from the cladding to the core. And also, we think the neck propagation should play some important role in this process, like it can influence the stress state in the core via interfacial load transfer. So this is our basic idea to develop a theoretical work. And first, let's quickly review two relevant theories. The first one is the classical shear leg model, which describes how the load is transferred at the interface and how the stress in the core is distributed in this core shell structure. Cox first studied this problem and gave such a solution to the stress distribution, which predicts the zero stress at the two ends of the core and the stress plateau in the middle part. Due to the stress plateau, we can expect a random fracture in the core, in the middle part. But this cannot explain the controlled fragmentation in our experiment. So that's exactly why we introduced this theory of neck propagation. Hutchinson and Neal first gave a systematic study on the neck propagation phenomenon for several different materials. And here, for simplicity, we just take the simplest necking material, which is nonlinear elastic. And in the steady state neck propagation, actually the material should satisfy this condition, which means the shaded area S1 should be equal to S2 in this engineering stress versus stretch plot, which is also known as Maxwell construction. So in our model, we combine the classical shear lag model and neck propagation and fracture together. We also consider both the core cladding system and film substrate system. The core and the film should be linear elastic brittle materials, while the cladding and substrate are ductile material. And for simplicity, we assume this rigid flat plateau shear sliding law at the interface. In our analysis, we have three cases for the core cladding system. And the case one happens when this failure stretch of the core is smaller than or equal to lambda b, which corresponds to this local maximum in this stress stretch plot. And in this case, actually, the solution is identical to that of the classical shear lag model. And we can see there is a stress plateau here in the middle part of the core. So that means random fragments can be expected in the core. And when the failure stretch is larger than lambda b, we come to case two. In this case, based on some analysis, we know that between the sticking zone and the shear lag zone arises another region DC. And the region DC turns out to be a sliding zone with opposite shear direction as to that in the shear lag zone. This region DC is referred to as the reverse shear lag zone. And also we can obtain the stress distribution in the core, where we can find that there is a peak tensile stress at point C. This is actually a very important feature because that means the fracture in the core in this case is deterministic rather than random. So this is the key to the controlled fragmentation. And based on strength-governed failure criterion, we can obtain the solution to the fragment size L frag. And here LCC is a feature size related to the material properties of the core. Also, for brittle materials, since the ratio of strength over Young's modulus is very small, so we can obtain an approximated solution here, which is in terms of the strength and the radius of the core, as well as the interfacial shear strength tau int. And from our theory, actually, we can get a condition for the controlled fragmentation. That is, the failure stretch should be between the lambda b, which is here, and lambda n, which is the stretch in the neck region of the cladding. And also we found the previously reported experiment measurements are all consistent with this condition. So this also verified our theory. And the case 3 is when the failure stretch is even larger than lambda n. Actually, this is an extreme case that rarely happens in experiments, so we will not discuss in detail here. And basically, this is the evolution process of stress distribution in the core in this case. And our theory can also be extended from the core cladding system to this film substrate system. The major difference between the two is that in the first system, the core remains always flat during deformation. But in the second system, the film becomes curved after deformation. So to describe the deformation of the film, we need to introduce this curved axis S. And after that, the rest analysis will be similar to what we have discussed. And also we can obtain a solution to this fragment size in this film substrate system. Next, we will discuss some issues based on our theory. The first one is about the position of fracture in the core. Based on our theoretical results, we found the position of the fracture can be either within the neck region or after the neck region in this case. However, in both cases, actually the difference from the fracture position to the necking front is always limited. So that means the fracture is always following the neck propagation. And as we have mentioned, the fragmentation size for brittle materials can be approximated as this form for core cladding system and this form for film substrate system. These forms actually inspire us to reduce the fragmentation size by increasing the interfacial shear strength tau int and decreasing the feature size. For example, the radius of the core and thickness of the film. To verify our theory, we also conducted finite element simulations. The left figure shows that the theoretical predictions indicated by the dashed line and the FEM results indicated by dots are very close to each other. And the right figure shows the fragmentation size has a very weak dependence on the Young's modulus. So that means our theory and our method can be applied to a wide spectrum of brittle materials with different Young's modulus. And these two figures show the corresponding results for the film substrate system. And then the conclusions are basically the same. Experiment data also verify our theory. For example, this measured average size of the micro rods are found to be linear to the diameter of the core, which is consistent with our theoretical prediction. We also use Raman spectroscopy to measure the stress distribution in the graphene film, and the results confirmed the existence of the predicted peak tension. And this is from our theoretical predictions. Then we can summarize this work. We can see in the conventional shear lag model, there is only a shear lag zone, while in our model, it shows under the influence of the neck, there should be an additional reverse shear lag zone. And this reverse shear lag effects will result in peak tension and thus the controlled fragmentation. So that's our major findings in this work. So in conventional wisdom, both the necking and the fracture are to be avoided in material engineering. But here we can use them to manufacture micro and nanostructures. And in this work, a theory of controlled fragmentation by co-drawing has been established, combining classical shear line model and the theory of net propagation. Net propagation induces a reverse shear line effect at the interface, leading to a peak tension in the brittle material. The peak tension builds up as net propagation until fracture of the brittle material, and we can obtain a highly uniform fragment size. Our theory also suggests the fragment size can be reduced by increasing the interfacial shear stress and or decreasing the dimension of the brittle material. So thank you for your attention.